All right, I know that looks very messy, but 10.6 phase change thermo. And worksheet do number 1, 3, and 4. Really, all of them are good. Number 4 is really long, and number 3 is the second longest, and these are very short. If you wanted to, you could do number 1, 2, 4, but then just tell me on number 3 what you have to do, like what steps. You'll know what I mean. Number 4 has like 5 steps. I gotta do this, 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 this. Okay. Number 3, I think, has 3 or 4 steps. You can just tell me, well, I gotta do this, 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 but you don't have to. You can like skip the math on that and just tell me what you would do, but then just do number 1 and 2. Well, you'll see what I mean. Okay, I'm making this sound crazy. So when you do the homework, do number 1 and do number 4 first. Then after you do number 4, then kind of look at 3 and 2, and you can decide whether you'd like to do the shorter one. Just want to make sure you understand it. It's not such a big deal. I'm going crazy about this. Okay. Yes, I tried to make the other video for the advanced class, and I got carried away with a lot of other information. But I'm going to show you one thing before I start. I want to show you one thing that's also important. But the notes we'll look at will be 10.6, and these 4 pages, or 4 little blocks here. Okay. First, let's talk about, you see in the very beginning of it, there is something called a heating curve. Now, they call this a heating curve, and whenever you see a heating curve, it will always be true for a pure substance. What do I mean by a pure substance? Like, for example, H2O. Water is a pure substance. All throughout ice, it is only H2O, H2O. Liquid water, H2O. Steam, H2O. Okay, the molecules don't change when it goes from solid to liquid to gas. Okay, iron, any element would be a pure substance. Okay, water, iron, any material like that. Now, salt water would not be a pure substance. It would be a mixture. It would be 2 chemicals together, salt dissolved in H2O. Okay, so another way to say it, if it's an element or a compound, then it's a pure substance. That's an easy way to remember it. I could have just said that right off. So any element, any compound, will have this little pattern that it follows. And I'll explain what the heating curve is. The idea is you start off with a material, and does that, yeah, I guess you can see it pretty good there. You start off with a material in the solid state. So let's just say that you went to like a walk-in freezer, and I put a bunch of pieces of ice in like maybe at a restaurant or like a Costco or somewhere like that. You go in there, there's a giant freezer, not a refrigerator, but a freezer, so it'd be really cold in there. Walk-in freezer, and inside there you get some ice, and you go inside, and inside the freezer you plug in like a little hot plate. Okay, so you plug this in, and you're going to heat it up, kind of like what you see on a stovetop. Okay, now we're going to put a thermometer inside this to see what happens as it changes it melts and so forth. Okay, so you start heating it up. Now, on this top, down here we put, let me see, here's temperature. Sometimes people put time down here, but it is time. You can put time there, but it really, as long as you're doing consistent heating. Like, for example, let's just say that before I put this ice on here, I turn this all the way up to high, okay? Now I start it. When it's all the way up on high, at that very moment, it stays on high the entire time. The idea is that the source of the heat stays constant through the entire time. Now, if you had fire going on below it, as long as the coals are the same, you keep them heated up, it'll be better with electronic to keep the temperature just right. So it's just going to be, well, actually, we're going to be adding as much heat as we can to it. Like another way it could be written, like maybe it's giving off, we could give a number like 100 joules per minute, or 100 joules per second. So every second, 100 joules of this are being added to this, okay, to try to change it. So you will see time down here with constant heat. Okay, and it can be kilojoules or whatever added. Constant heat added. Okay, so it must be constantly heated. Now, all right, so here's what's going to happen. So let's just say also I'm gonna pick temperature. Let me get temp. Let's start at a low temperature, like let's just say for ice. Say we have ice. Let's just go to -5, because you know that at -5 ice is solid. It's not going to be a liquid. Okay. What's going to happen is the -5 ice, as you heat it up, it will go. The temperature will rise. Now, at one point, what's going to happen is this is going to happen. Interesting. You get a straight line. So what we're saying is we had not stopped adding the heat. We had not stopped adding heat. We're still adding the same amount of heat every second, every minute. But the temperature went up -5, -4, -3, -2, -1, 0. Aha. At 0, look at what happens. Now, do you know what happens to ice when you heat it up? Once it gets to 0, what does it start to do? It starts to melt. You probably know that. It melts. It goes from a solid to a liquid. Now, I know I mentioned this on another video. All right, then what's going to happen after that, after all of it is changed from solid to liquid, it's all 100% water now at this point on the graph. Now it's going to be heat up on to be, well, let me make it the graph a little bit different. I'm going to make it like real straight up like that. It's going to go up. Well, no. I'm sorry. I am going to go more like this. Yeah. It's going to go up again until you get to, guess what? 100. The boiling point. Okay, I guess it's going to go a little bit higher. Then it's going to stay straight like that. Then it's going to go up again. Okay. So you get this little pattern for any pure substance. I'm going to explain about this. Now, I think I did already mention this in a video before. Solid to liquid here. Here it's a liquid going to a gas. And here it's only a solid increasing its temperature. Here it's only a liquid increasing its temperature. And here it's purely gas. At the end of that line, it's all steam. And then you're heating up the steam to go higher and higher to 110 or whatever we'll just say on the graph. However high it goes, it'll keep getting hotter and hotter. Okay, so that's what goes on in a heating curve. All right, now I know I realize now that was gone over in an older lesson. But now, and also I believe I talked about the interesting thing at this point is that even though you're adding heat to it, the temperature is not increasing. So what's going on? Where is that heat going? They used to call that latent. The word latent means hidden. The hidden heat, latent heat. Where is that heat going right there? Well, what it really means is all of the heat is going into breaking or weakening or breaking the intermolecular forces. Here, at the beginning of this dot, all the ice is hydrogen bonded. Every H2O molecule is H bonded to another H2O molecule, to another H2O molecule in a perfect crystal, which I am not drawing a perfect crystal here, but anyway, a perfect crystal structure all around. So that's going to all be perfect in the ice. Well, when you get from there to there, what you're doing now is you're weakening so much that they're leaving the crystal state. So that is being weakened, that's being weakened, that's being weakened. And now these molecules can just swirl around and move around through each other, around and through each other. They're not locked into place anymore. So you had to pull them apart good enough, have enough kinetic energy. So that your energy is breaking that crystal structure. All the heat is going into breaking the crystal structure for every single molecule. At the end of it, all the crystal structures are broken, and you have water molecules that are still like magnetically, if we'll call it that, or electrically attracted, but they're very loosely attracted. They can move, they can shift around easy at this point. Now, you're heating that water up faster, higher, faster motion, until finally they completely separate out. H2O, and that heat is called the heat of vaporization. And over here, I forgot to tell you, this is called the heat of delta H fusion. So heat of fusion, you'll see that in a moment. It's the heat required to change a solid all the way to a liquid while it's at its melting point. So if you get a material to its melting point, like if I take ice all the way up to 0, just to say right before any melting occurs, right when you get to zero, the solid ice went from -5 to 0. Right at 0, now any heat we add is going to go to breaking off the molecules. Instead of increasing the temperature, you get up to 0. Now every bit of heat you add will break off one H2O, another H2O, another. Well, I say break them off, but it will break them out of the crystal structure. We'll say that. It breaks them out of their locked position in the crystal structure. Like if they're locked in somehow, now they're still attracted, but they're no longer locked into place. Drawing my knuckles like that. So like in the solid, every molecule is like hooked together with another molecule. But then after the liquid, now they're no longer hooked together, and now they're attracted, kind of like two magnets that are not yet in touch with each other because they're moving so fast. Okay, but anyway, heat of fusion is the heat to go from solid to liquid. Then you heat it up, and then heat of vaporization will get you from liquid to gas. Now that I've done all this, I'm going to actually change the graph a little bit and show you some important numbers on the graph. And I didn't draw that too good, did I? That should have been really a straight line. All right. In real life, you do this in a lab, and it won't look perfectly straight because maybe you're not really heating it all right, or our thermometer might be that great. There's all kind of little factors that we forget about. Okay, heat of fusion, heat of vaporization is used during this period of time, from there to there, and from there to there. Now, the specific heat, remember specific heat. Okay, Q is mCT2 minus T1. Well, here's what makes this even more fun, and you'll like this. There's a specific heat constant for water, and there's a specific heat constant for ice, and for steam. So, for water liquid, the specific heat is 4.184 joules per gram degrees Celsius. Maybe you remember that number, okay? I don't remember what it is for water, for ice, solid, and H2O liquid. Gas, I'm sorry. It changes. I want to say it's something like 1.8, or maybe 1. I don't know. Let's just say 1.7 and 1.8. I'm just going to make up some numbers. But anyway, it might be 2.8. I don't even know. But the point is, all of these are different. So, if I want to calculate the heat that I need to go from -5 to 0 for ice, here it's solid ice, right here, a block of ice, from -5 to 0, I have to use the specific heat value that is assigned to ice. Actually, it's on the paper. I said I didn't know what the numbers were. They're on here. It says it's 2.1 liquid. Gosh, it's on number letter D. Vaporization, I got gas. Liquid, 4.184. And then for ice, it's 2.1. And I don't know what it is for steam. So, okay, ice is 2.1. Sorry about that. 2.1. I'm going to have to find that out because I got to do the problem today. Okay, and then for gas, it'll be some other number. Okay, but anyway, all right, that's important to know. All right, so let's go to the math now. Oh, but before I go to the math, I better tell you one more thing. Okay. Actually, I might not have drawn my graphs right. In fact, let me look it up right now. What is the specific heat for steam? Okay, the specific heat of steam is, and I've seen it before, so I would know. Okay, it looks like 2.0. For steam, it's 2.0. So it's really close to that. It's actually 1.99. We'll put 1.9 just to make it look different. So well, it is different. 1.9 joule per gram degrees Celsius. By the way, they can also write joule per gram Kelvin instead of Celsius because a Kelvin is the same size as a Celsius degree. So it's the same number. So don't be fooled. I don't think they'll do that on AP or something. I'm not going to plan to do that in general, but if you saw joule per gram Kelvin, that number is the same as joule per gram Celsius because Celsius, Kelvin are the same. Okay, anyway, if I want to go from, in this area, you're a solid, so you'd use the QMC delta T for the solid. Here, QMC delta T for the liquid. And here, in this last section, if I had one, QMC delta T for the steam, gas. Okay, whatever, gas. All right, here we go. So let's start off. Oh, and I said I was going to tell you something and I forgot to tell you. Okay, now the heat of vaporization for water. Let's just write that down too. Delta H, well, fusion, and delta H vap for vaporization. Okay, heat of fusion, the heat needed to melt ice, is equal to 334 joule per gram. And then for vaporization, it is 2260 joule per gram. Okay, now, here's what I want to show you. So here's a neat little thing, a little side note. Well, sort of, but important for AP especially. Maybe for general, it's a good thing, it could be a bonus. But look at this. Notice the heat of fusion line is this long, but the heat of vaporization is longer. Okay? Okay, that one is shorter, that one is longer. That means something. That tells you that as long as heat's being added, remember constantly as time goes by, it takes longer time. In other words, it takes more heat to change it from a liquid to a gas than it does to go from a solid to a liquid. This is longer. That means the heat of vaporization is a bigger number. And look over here, heat of vaporization is 2260, wow. But heat of fusion is 334. It's a lot longer. So I just made this up, this drawing, but really that would be very short compared to the vaporization line. Okay? And why is it so much? Well, think about it. If you want to take liquid and break every molecule completely apart into a gas, that's what's going on with heat of vaporization. Heat of fusion, all you had to do was just take them out of where their locked positions. But now for heat of vaporization, it means they're so far away that they couldn't even attract back to each other like magnets. Every molecule of water is moving so fast, it has to be a long, long way apart. Okay, the other thing, it's also true about the Q lines. You can tell the specific heat based on the, because the mass and the temperature, the mass will be the same. All I wanted to show you is that the specific heat is directly related to the curves you see right there. And so if you see, I might not have drawn it right, I'll figure out in a minute. If you see, whatever the slope of the line is, if you have a really high slope or a low slope, okay? A high slope would actually mean that it heats up really quickly, right? So that means your specific heat value will be small. A more flattened or a lower slope, less inclined, would mean it takes a longer time to heat it up. So it has a higher value for a specific heat. So I don't know if I did it right on mine. 4.184, for the liquid, 4.184, the line is really nearly flat down. So yeah, it took a long time. But for the solid, it was only 2. It shot up quicker. Yeah, so that makes sense. I did it right. This one would heat up faster because it has a smaller specific heat. But once it's in the liquid state, it takes more energy to heat it up. Okay, notice that. And I don't know, that one is probably about the same as the last one, I guess. 1.9, yeah, those are about the same there. Okay, so that's an important thing. All right, now here comes the math. Okay, so here's the math. First, I'll do letter A, and it says, calculate the amount of heat in joules required to melt 275 grams of ice at 0 degrees Celsius. And it says the heat of fusion for water is 6.02 kilojoules per mole. Now, you're going to notice something. Here I put the heat of fusion in kilojoule per mole. Over here I have it in joule per gram. These are the same numbers. In fact, you could convert one into the other. I don't know if I'm going to do that for you. I don't think I will. Maybe in class I could show you. But I could change kilojoules of heat to moles of H2O into joules of heat per gram of H2O. AP students should know how to do that. And you're the only ones that would be asked to do that anyway. But I can show you in class. Okay, but anyway, we'll use this value. So sometimes people like to use an equation for this. We have QMC delta T and we have heat of vaporization, heat of fusion, and QMC delta T to QMC delta T. There's three of those. And they make up this equation. If you want to use it, you can, but I don't really do it so much. But Q is equal to N, the number of moles, times delta H. That could be an equation. Now, if delta H is in moles, then you multiply it by mole. If delta H is in grams, it could be the mass times delta H. So Qn delta H or Qm delta H. You could use those right here. Like you could say Q equals N delta heat of fusion, or Q equals N delta heat of vaporization up there in that line and that line. So you got one calculation, two calculation, 3, 4, 5 equations to do this problem. It can be a lot of work. I don't think you really need to use those equations, these two, but if you want to, you could, okay? And you can plug them in if it makes you feel better to do it. But I'll show you. I'm going to do A without the equation. So it says A, what is the heat needed to melt 275 grams of H2O at the melting point? So remember, the reason they say that is H2O solid. It might have started at -5. Well, that doesn't really matter. We have to first get it up to 0, and it's all H2O solid, 0, right before it melts. Now, how much more heat do we add to go from there to there? And it's 6.02 kilojoules per mole. So all you do, first, I'll go from gram to mole of H2O, and you do that the same way you did all semester. You look on the periodic table, and you know that water is, H2O is 1H plus 2 O's. That's going to be 18.02 gram per mole. Then what you do is from moles, I can now go to kilojoule. I can convert from mole to kilojoule of heat by using that number, I forgot, 6.02. So 6.02, I'm sorry about that, 6.02 for every 1 mole. And my answer is going to be, well, I can write it below it, I guess. 275 times 6.02 divided by 18.02 is 91.9 kilojoules of heat. So if I took ice, it doesn't matter what temperature, it could be -200. But if I had ice and I heated it all the way up to 0, it's still ice, not yet liquid at all ice, right about to melt. Then if I had this many grams of the ice, a big chunk, I'd have to add 91.9 kilojoules of heat, and then it will completely melt. Okay. All right. Now, here's another interesting thing to tell you about this question. In the question, when you read it, you might be wanting to think, I'm going from H2O solid to H2O liquid. Okay, solid to liquid. Okay, that's the heat of fusion. Sorry, heat of fusion. If I were going from H2O liquid and changing it to H2O solid, guess what? Guess how much heat is going to be needed? The exact same number, but now it's going to be a negative value. Okay? So you see that as far as like exothermic, endothermic. You can think about it. I had to change a cable here. If you go from solid to liquid, do I need to add heat? Yeah, you got to add heat to melt something. That's endothermic. But if you go from liquid to solid, that's exothermic. It will release it. It's the same exact number and the same problem. So, if you're told that you need to calculate the heat needed to melt 275 grams of ice, you use 6.02, the heat of fusion. If you're told you need to find out the amount of heat that is released when liquid water, if I had 275 grams of liquid water and it freezes to ice, how much heat is released? Well, then it will be the same value, 6.02, but it will be negative 6.02 kilojoule per mole. So it will be in the exothermic direction. All right. Now, that was letter A. Next, it says vaporized gold is boiling point 3080. B, you do the exact same way. This time, it just says you've got gold, 350 grams of gold. You want to vaporize it. You're going to use heat of vaporization. So I'm just going to say 350 gold, change gold from gram to mole, then times 310. But let's see. Letter C says calculate the heat. Let me do that one. Let me go to C. And I guess I'll erase this. That's going to That's going to be a lot like what I just told you a moment ago, actually. This is like what I just told you on A. C. Calculate the amount of heat that is released when 45.45 grams of ethyl alcohol freezes at negative 130. It's melting point, freezing point, okay? Freezing point and melting point mean the same thing. And it's 109 joule per gram. All right, this one, they gave you the heat of fusion in an easier term. So 45.5 grams of ethyl alcohol is actually ethanol. You don't have to worry about the formula. AP students should know ethanol. You know, methane. Ethane is C2H6. So it's C2H5OH. You don't have to. You can figure that out. Or you can write C2H. Yeah, that's how I like to write it. Yeah, that's how you'd write it down there. All right, ethanol. Now, when you change that into heat, well, look at this one. It says, if this is, what is it? We're going from, when it freezes, that means we're going from a liquid to a solid. So I'm going to use heat of fusion. And I look, I look like I'll make the screen go off, but oh well. Heat of fusion is 109 joule per gram. I can go from gram straight to joule and just use 109 joule per gram for every 1 gram of C2H5OH. But now, technically that's got to be negative because liquid to a solid is exothermic. Okay? The easy way to know it is, I always think, what is endothermic? When I go from liquid to a solid, do I need to add heat? Adding heat would mean endo. Do I have to add heat to water to make it freeze? No. You add heat to ice to make it melt. So that direction is endothermic. So that means the other one has to be exothermic. And exothermic always has a negative value for the heat. Negative 109. So 45.5 times negative 109 is going to be 40. Wow. Well, that makes sense. 4,950. Negative 49050 heat released. That also just gives me a little, well, if you're asked to calculate the amount of heat released and you don't, if they say, what is the amount of heat released, and they just put that, you would be okay. But if they say calculate the amount of heat involved means, is it going to be, make sure you have the negative sign. So it's probably better to have the negative sign anyway. If it's ever exothermic, negative, endothermic, positive. Okay, let me get that thing right. Okay, now for the mega problem. And as I do this, I might try, I wish if I had it worked out somewhere. I'm looking at the time here, how long it will take me. I'm going to try to do it kind of quick, but I'm going to show you every step if I can. All right, let's just say I'm going to change the problem a little bit. And letter D says, determine the total amount of heat required to convert 25 grams of ice. It says at negative 5 Celsius into steam at 100. Maybe I will just do what it says on the paper. I was thinking of going all the way up to 110 and going to the other one, but the other specific heat. But let's just do this first. So let's go from ice from negative 5 ice to steam at 100. All right, when I'm doing a problem like this, on your worksheet or on a quiz or test, you might not be given water. Instead of H2O, specific heat of H2O solid, H2O liquid, H2O gas, heat of fusion of H2O, heat of vaporization H2O. 5 values. They might have given you something like gold. They could tell you the specific heat of solid gold, liquid gold, gaseous gold. Yeah, there is gold vapor. Heat of fusion of gold and heat of vaporization of gold. It doesn't matter. But what you need to do is you need to draw a little graph like this. I recommend whenever you're doing these calculations, draw that line. Then make a mark here and a mark there. This is always the melting point. This is always the boiling point. They'll have to tell you the melting point and boiling point, or at least whatever you need. And then, of course, so that's the melting point. For water, it's 0. The boiling point is 100. By the way, melting point can also be freezing point. So if you want to call it the melting point or the freezing point, that's more like something they could do, just playing around with the words a little bit in AP. I mean, they're different words, but they're the same thing. They want to make sure you know they're the same. Okay, so I'm going to go from ice at -5 to steam at 100. Okay, we'll put a little at like that, and that'll be good. At 100 degrees. Okay, so here's what I do. On my graph, I have to write down, okay, what is the melting point of ice? 0. What is the boiling point of H2O? 100. Where am I starting? -5. Okay, so I'm going to start right there. Where am I going to end up? Steam at 100. Okay, here is 100. Here it is a solid. Okay, solid changing to liquid. Liquid, here it's a liquid changing to gas. Okay, so where will it be steam? It will be steam right there. Right here is purely steam, and now it's going to heat up if you keep adding it. So what they're saying is you've got to calculate this, 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 and this. All 4 values, and then you got to add them together. Now, when I give you a problem on a quiz or homework, let me take it back. On a homework, I'm going to make you do a mega problem, make you go all the way from there, 2, 3, 4, all the way up to here, 5. If you can do that, you can do any problem. But really on a quiz or test or even on the AP exam, most likely they would only ask you to do probably just 2 steps, like from there to there to there, maybe 3. They might ask you to do 3, but most likely 2 steps. Okay, but I'm going to do one that has 4 steps. So if you want to label the steps, you can do that. Number 1. That's what I was telling you on for your homework, do number 4. And then when you go back, then you can look at number 3 and just label the steps, and you don't have to do the math. That'll make it easier for you. I mean, if you want to do it, you can, but I don't want it to be a busy work. But I do want you to do this mega problem that you'll see. So number 1, I want to go H2O solid to solid. I want to go from -5 to 0. Right there, that first section, -5 to 0. I'm writing it really messy. -5 to 0. To 0. That's the first step. Solid, -5 to 0. How do you do that? Q equals MC T2 minus T1. So the heat will be the mass, 25, times the specific heat, which is 4.184 joule gram degrees Celsius. That's the value for H2O solid. Liquid. No. Oh, I'm wrong. That's not the one for solid. I put liquid in there. I have solid H2O, so I gotta watch out. Thermo is a lot of bookkeeping. It's 2.1 joule per gram degrees Celsius. Okay. All right. Now, oh my goodness, I don't believe this. I hope I'm not gonna have to stop in the middle of the problem. I might have to, but all right. So the temperature final is going to be 0 minus the initial is -5, so it's a +5. So 0 plus 5 right there. Minus -5 becomes 0 plus 5. Okay, so 25 times 2.1 times 5. 260, really 260 with sig figs. 260 joules. And I did not show the cancellations. If you want to show them, these are all Celsius. So the Celsius would cancel, gram, but you're left with joules. Also, you see the number is a positive value because it was 0 minus -5. So that means it's endothermic, and that makes sense. You have to add heat in order to get from a solid to a liquid. Oh, I'm sorry. To get from solid low temperature to high temperature. I had a problem with my computer. I'm trying to do it two things at once. That's step number 1. Step number 2, now I'm going to go, you heard it. From the heat of fusion, I'm going to take 25 grams of ice, and I just want to go from solid to liquid at 0. So H2O solid, now it's H2O liquid. So 25 grams. Now I have to use the delta H of fusion of water. 25 grams of H2O. Heat of fusion of water is 334. 334 joules for every 1 gram of water. So 25 times 334 is 8350 joules. Okay, so 8350 joules to go from H2O solid to liquid, to can't read my bad writing there. Okay, and then 260 to go from -5 to 0. All right, we've gone from there to there, now there to there. Now we got to go from this part and increase to 100. So part 3, we're going to go from H2O liquid. It's all liquid now, and we want to go from 0 to 100. So Q equals MC T2 minus T1. Now, I could have put up here C solid and Cl for liquid. That way I'll remember to use the liquid water and not the other one. All right. So, sorry, I have to fix this. Okay, so the mass is still 25. See, the mass never changes. 25 grams, 4.184. And then the final temperature is 100 minus 0. And so I won't put in all the number of units there. Let's go a little bit faster. And it's 10500. I'm doing sig figs. 10,500 joules of heat is needed to go from 0 liquid all the way up to 100 liquid. It's still all liquid. And then the last step will be to go from all liquid, H2O liquid water, and turn it all into H2O gas, which is steam, at 100. It stays at 100. So on the flat lines, you're just using the heat of fusion. Now, if you want to use the equation, Q equals M delta H, you plug in the mass, plug in delta H, just multiply. But I like to do it as a conversion, which is really the same thing. I have 25 grams of water. This time it's going to be liquid water. Yeah, it really will be water. Okay, not ice. And I'll go from gram to joules by using the heat of vaporization. Delta H vap is 2260 joules for every 1 gram. Now, I'm going to just multiply those. 25 times 2260 is going to be a big number. 56,500. So 56500 joules. Are we finished yet? No. The question was, determine the total amount of heat. So I need to add all 4 numbers together. Step 1, step 2, step 3, and step 4. So I'll try to do it here in the corner. I guess it'll fit. 1, 2, 3, 4. 260, 8350. Well, I'm not really lining them up. 10,500, 56500. I'm going to put them on the calculator. I hope I'm doing my math. 260, 8350, 10,500, 56500. It's 75,610, and it looks like I've got 600. 75,600 joules, and they were all positive numbers. Now, if I did the entire problem backwards, I could say go from 25 grams of steam at 100 all the way to -5 ice. Then you do the same thing. You calculate that, but every number would be negative. You know, you put in every number. For the delta H will be negative, that will be negative. The temperatures, of course, will be reversed. The T1, T2 will end up being negative automatically. You don't have to do anything to those. But that's how you do it. Okay. Again, I want you to do number 4 on the worksheet. And now that I said that, if you're watching this far, do number 1 and do number 4. Okay. Now, after you do number 4, just look at number 3 and just tell me on number 3, oh, I got to do these steps. I got to go from here to there, there to there, there to there, whatever they are. Just label them, but you don't have to do the math. You'll see the answer key when it comes around. So, I know I went quick through that last math bit, but I wanted to get it all done, and I think we got it. So, this is a good one, and I want to tell you that AP students, they have been asking about stuff like this a lot in the past 10 years. Like maybe 4 or 5 times they've asked you to do this on it. And they're probably only going to have you go like 2 steps, like from this point to that point. Just add that, calculate that, calculate that. Of course, they'll give you every value. So you got to know which ones to use. That's the thing. If you know what value to use here, heat of fusion, not vaporization. Or from there to there, I use Q, MC, delta T, C for the liquid, not for solid or gas like I was trying to do on that messed up problem. All right, I'll see you guys later then.